We're going to learn about Lewis structures. Lewis theory is a theory of bonding, and it helps to explain why certain atoms will bond together and form a molecule and why other atoms will not. And it helps us to predict formulas of compounds and all kinds of good stuff. It does not work for everything. It's not a comprehensive theory, but it works for the more straightforward, simpler things, and it's relatively easy to understand, and so it's the model we're going to talk about. So what a Lewis structure does is it shows the valence electrons and how they are arranged among the different atoms in a molecule. What are valence electrons? The electrons that are on the outside of the atom. How do we determine how many valence electrons an atom has? Positive and negative charges are related to that, but there's something on the periodic table that tells us. The number of protons tells us the number of electrons. Has to do with some of the numbers at the top, the group numbers. Okay, so for the main group elements, the group number tells us how many valence electrons are in an atom. So chlorine being in group 7A has 7 valence electrons. Boron in group 3A has 3 borons, 3 valence electrons. Okay, so that's really important, is to be able to look at the periodic table and identify how many valence electrons something has. And what is important in these Lewis structures is that atoms achieve noble gas electron configurations. And we did not talk about electron configurations, and so I'm just going to change this a little bit. Achieve the same number of valence electrons as a noble gas. How many valence electrons does the noble gas argon have? 8. How about neon? How about helium? Trick question. How many electrons does helium have? 2, right? Remember these blue numbers here? Those are the numbers of protons and electrons. Helium is one of those little guys on the periodic table. He only has 2 electrons and 2 protons. So he can't possibly have 8 valence electrons, can he? No, so he only has 2. So kind of like hydrogen, who's an exception to lots of rules, helium is an exception to some of the rules as well, because he's like, the little baby brother. So what these other elements are going to do is they are going to combine in molecules so that they feel like they have 8 valence electrons, or for the really small guys, hydrogen just wants to be like helium. Okay, and in my weird chemistry land, right, I think of the noble gases as being the cool kids in high school, right? The in-group that everybody else, at least secretly, kind of wants to be like. And so you dress like them, and you hope that maybe you can sneak in. You want to look like them. The electrons are on the outside of the atom. They're kind of like the clothing that the atom wears. And the electrons can change. We can form ions by gaining or removing electrons, and atoms can also share electrons with other atoms. So it's a little bit like the clothing. Now the protons are what makes an element a particular element. Carbon has 6 protons. Even if it gains or loses electrons, it still has 6 protons. That's the soul, the spirit of it. You can't change who you are by cutting your hair or dyeing your hair or piercing something or wearing funny clothes or anything like that, but you can change what you look like. And so the atoms can change what they look like, and they want to look like a noble gas. So for most of the elements, they're trying to be like most of the noble gases with the 8 valence electrons. The littler ones are just trying to be like helium. So let's look at Lewis structures for individual atoms and for ions. And so it shows how valence electrons are arranged. And here's potassium, the ion. How many valence electrons does potassium, the atom, have? It has 1. And so if we draw a Lewis structure for potassium, we use a dot to represent the valence electrons. It's the electrons that are on the outermost of the atom. The valence electrons are the ones that come and go. So here is potassium. It's got 1 valence electron. What kind of an ion does potassium form? It's right here. A +1, right? A +1 ion. When it forms a +1 ion, does it gain an electron or lose an electron? It loses an electron. So what happens is the potassium atom loses that 1 valence electron, and then it becomes a positive ion. Now you're saying, but I thought they were trying to get 8. Why is it going to 0? Well, how many electrons total does potassium have? 19. Oops, not the fat one. It has 19 electrons. So when it loses 1, then it has 18 electrons. How many electrons does argon have? 18, right? Argon has 18 valence electrons. We skipped the sections that talk about how the electrons are arranged. But basically they're arranged kind of in layers, if you put it real simplistically, like, the layers of an onion or something. And so this potassium atom with 1 electron in this outer layer, it's easier for it to look like a noble gas if it just takes off that little bit of a layer that it has, because underneath is a nice full layer. And looking at total number of electrons, we can see that by losing an electron, the potassium ion now has the same number of electrons as the noble gas argon. So it looks like one of the cool kids, and that's what it's trying to do. So bromine, the molecule, bromine the atom, how many valence electrons does bromine have? It has 35 electrons, but what group number is it in? 7. So 7 of those are on the outside. So when we draw a Lewis structure for bromine, we're going to put 7 dots to represent those 7 valence electrons. Bromine wants to look like krypton. It wants to have 8 valence electrons. It's got 7, so it needs to gain 1, right? When it gains 1 electron, then it has what we call an octet. It has 8 valence electrons. Just like if you have 4 people singing, it's a quartet, and if you have 8 people singing, it's an octet of people. So we have an octet of electrons, 8 electrons. These are the outermost electrons, the valence electrons. This has a charge, and so when we have something like this with all the dots, the minus sign can get kind of lost in the dots, so what we do is we put the brackets around it and put the minus sign on the outside. But when bromine becomes an ion, it will have the same number of electrons as krypton. And that is, obviously, in my chemistry land analogy is just something I made up. Atoms aren't really trying to look cool or anything. It's really about the energy, but looking cool helps us to remember. And what did we learn about bromine when it forms an ion? What kind of an ion does it like to form? We learned to count from the right side of the periodic table, 0, -1. All of these guys like to form -1 ions. The reason is that when they gain 1 electron, then they look like a noble gas. So that's why they form those ions. Any questions yet?
Sorry, Mrs. Stan, I don't understand
Okay, that's a good question. Where are these dots coming from? In a Lewis structure, we represent the valence electrons as dots. We don't want to look at all the electrons because it gets way too complicated. You know, you get something like iodine with 53 electrons. It's only the electrons on the outside, the valence electrons, that are involved in bonding. The rest of them are just staying on the inside. So it's like your jacket, your outer shirt might be important. Which underwear you're wearing doesn't really matter. So we're not even going to talk about the underwear, right? So those inner electrons are more like the underwear. Oh yeah, I didn't renumber this one.
Okay.
They gave me one set of stickers. So over here, when you look at the group numbers, just ignore the 1. So group 17, just erase the 1 in your mind. Group 7.
Okay.
So this is 8, 7, 6, 5, 4, 3, 2, and 1. So those numbers are related, but the periodic table on the other one has the actual A numbers. I should get up there with the Post-it notes again. They fall off after a while. Does that help?
Yes.
Okay, any other questions? So when we write Lewis structures, this is what we do. The group number, and those are the A numbers, 1A, 2A, 3A, etc., gives us the number of valence electrons. And we have bonding pairs, which are electrons that get shared between two atoms. There are also unshared pairs. These are called lone pairs because they're loners and they're off by themselves. Those are not involved in bonding. And we have something called the octet rule, which states that atoms, except for hydrogen, will be surrounded by 8 electrons in a good Lewis structure. There are things that Lewis structure doesn't work for, and so we're going to ignore those. We're just going to do things where the rules work. So let's look at fluorine. Fluorine is in group 7A, right? It has 7 valence electrons. So we draw the element symbol in the middle and 7 dots around. Now just by convention, and there's some other reasons for it too, we draw the electrons on the top and the bottom and the left and the right. We don't make like a circle or stick them all on one side. It's a little bit like dice. Have you ever played Monopoly with a 5-year-old? They roll the dice and they have to count all the spots because they haven't learned to look at it and say, oh, that's 3, or oh, that's 5. They don't remember the patterns. When we put the dots in this same pattern all the time, 2 on top, 2 on bottom, 2 on left, 2 on the right, we can look at it and see that there's 8 without having to count all the dots all the time. So this is fluorine. In order to be happy, the fluorine needs 8 dots. Is this fluorine happy? No. Here's another fluorine. Again, 7 dots. Where I draw the single dot really doesn't matter. If I put it on the right or the top, doesn't matter. It's just drawn here on the left so that it can be closer to this one over here. Is this fluorine happy? No. 7 dots, not happy. So this fluorine says, hey you, over there, give me one of your electrons. I want 8 electrons. Is this fluorine going to give up an electron? No. It's like, no way. Why don't you give me your electron? I'm looking for an extra electron too. I'm not going to let you have one of mine, then I'll be worse off. And so they argue for a while. And then they come up with a solution. Hey, how about if we share? So they get together and they each share 1 electron with the other. Now when you share something, it belongs to you and it belongs to the other person. My husband and I have 6 children. I have 6 children. He has 6 children. There aren't 12 children in my house. Thank goodness. There's barely room for 6. But there's only 6 children and yet we each have 6. So these electrons that are being shared get counted by each atom. So drawing mode, come on. So this fluorine counts all of those electrons as belonging to him. He's like, cool, I've got 2, 4, 6, 8. I've got 8 valence electrons. This is good, I'm happy. And the other fluorine can also count the shared electrons, and he's happy too because he's got 8. Fluorine is one of the diatomic elements, and this helps us to understand why, when fluorine is alone as an element, it forms molecules. Because this is a better state for the fluorine atoms to be in, because they now have this 8 electron business going on. They satisfy the octet rule. So what we're going to see is that the atoms come together and they will share electrons so that they can each get 8. Any questions? Yes? Pardon me?
Does that apply to every diatomic?
It does apply to all the diatomic elements, yes. So we have steps for writing these Lewis structures. The first thing is to add up the valence electrons from all the atoms, and we're going to do some examples. Then we're going to put a pair of electrons to form a bond between each pair of atoms, because something has to be sticking them together. And then usually the atoms are going to have noble gas electron configurations, in other words, 8 electrons. So we're going to take the remaining electrons and distribute them around so that we get an octet. So the octet rule applies to everybody except for hydrogen. For hydrogen, he has a special rule called the duet rule. So let's do water. So we've got 2 hydrogens and an oxygen. How many valence electrons does a hydrogen have? What group is it in?
1.
1. And how many does an oxygen have? 6. It's in group 6A. And the other hydrogen also has 1. So we have a total of 8 valence electrons. The valence electrons are going to be shown in the diagram as dots. So what we're going to do is we're going to say, well, there must be a shared pair of electrons between the hydrogen and the oxygen to form a bond, and there must be another pair here to form a bond. A chemical bond is just a pair of electrons that are being shared between 2 atoms. So we've got 2 here and another 2, that's 4 electrons. So we have 4 more that we can put. So we'll put 2 here and 2 there. The oxygen now has an octet, 2, 4, 6, 8. The hydrogens do not have octets, but they're too small. They can't handle it. They want a duet. So here the hydrogen has 2 electrons. 2 electrons makes it look like helium with 2 electrons. They're trying to look like the noble gases. And that's when you get your electrons arranged in the same way. So this hydrogen counts those 2 electrons. This is a bonding pair. And this hydrogen counts those 2 electrons. And the oxygen is going to count all of them. The shared electrons get counted by both, just like my husband and I each count all of the children as our own. Sometimes we connect the dots and write those bonds as a line instead of 2 dots. So you'll see that sometimes. You might see the Lewis structure for water looking like this. So what these lines are is just two electrons connected. We just connected the dots. Oops, didn't mean to do that. We connected the dots. Yes?
Can you explain each electron cloud limitation amount? Like, is it the numbers on the side of the gases?
The numbers on this periodic table do have to do with the arrangement of the electrons within the atom, but that's not something we've talked about, and we really don't want to talk about it. It's kind of crazy and complicated. What we're looking at would be the bottom number here, and the numbers here are applying to the far right side, and so as you go over, this number gets less, and that's how we get the 8, 7, 6, etc. Wonder what happened to the 8A sticker for that. Does that help?
Well, I also want you to explain you know how like your first cloud can only have 2 valence, and your second cloud can have 8.
Mm-hmm.
Your second one can have 8.
We're not going there in this class. Okay, you're asking about the S and the P orbitals and the different levels, 1s2, 2s2, 3s, you know. We're not going to talk about those. I'd be happy to talk to you about it outside of class, but I don't want to confuse everybody else. Okay? So if you've had chemistry before, you may have heard about those. There's a very specific way in which all those electrons that are not valence electrons are arranged, and it's called an electron configuration. And if you take 3A, they'll teach you more than you want to know about that. Any other questions? Let's do PBr3. I need to edit these slides. So we're not looking at that. We're just going to do PBr3. I'm going to stick to the very simple molecules for you guys on the exam. So when you have something like this, it will either tell you what atom is in the middle, or something like this where there's 1 phosphorus and 3 bromines. The one that there's only one of, you put in the middle and you put the others around. Generally speaking, the molecules are very symmetrical. The lab we're going to do with the molecular models is nice because the model kit is set up so that there's only one way that you can connect them, and that happens to be the correct way. So that's why that lab is really helpful. So here we've got 3 bromines and a phosphorus. We need to figure out how many dots do we have to play with. Bromine. We've got 3 bromines. Bromine is in what group in the periodic table? Group 7A, so it has how many valence electrons? 7. So we've got 3 of those, and they each have 7. What about phosphorus? 5. It's in group 5. So we've got 3 times 7 is 21 plus 5 is 26. 26 electrons. So first, we'll make a bond between each pair of atoms. So there we've got 6, and then we'll start distributing the rest, and I like to just count while I do it. So I've got 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm trying to give each atom 8 electrons around it. So these shared ones represent single bonds. Each of them, though, is 2 electrons. And so we see bromine has 8. Each of the bromines, oh, I didn't mean to do that. And the phosphorus has 8. And so this is the Lewis structure for phosphorus tribromide. Any questions? Let me show you this one in a slightly different way. So phosphorus, we determined, had 5 valence electrons. So I can put 1 on each side, and then they have to pair up, so there's 5. And bromine had 7. The bromine is trying to find an electron. It would be fine with someone giving it an electron to be an ion, or it could share. So the bromine comes up to the phosphorus and says, hey, can we share electrons so I can have 8? And the phosphorus says, oh, sure. So they're going to share. Now that bromine's happy, the phosphorus isn't happy. Where there's one bromine atom, there's probably another. Here's another guy over here. He's got 7 valence electrons. He's looking for another electron. So he comes up to the other side of the phosphorus and says, hey, will you share your electron with me? I'll share mine with you. And the guy says, sure. That bromine's happy. Is the phosphorus happy yet? No, he's getting happier, right? He's getting closer, but he's still not happy. So enter bromine atom number 3 with his 7 valence electrons. And the phosphorus shares with the bromine, and now everybody's happy. Isn't that kind of cool? Kind of cool? A little bit? I think it's crazy cool, but then I'm a dorky chemist, so. But this is why molecules form in certain combinations. Why water is H2O and not HO or H2O5 or some other combination. Because in that particular combination, the atoms are happier. Really, they're at lower energy states. They're more stable, right? Things that are low to the ground are more stable than things that are up on stilts and all tilty, right? So they're getting lower in energy, they're going to be more stable. Let's do some other ones. Draw Lewis structures for these guys. So as I'm explaining this to you, I'm thinking that maybe that last way where I drew the atoms with their electrons and showed how they shared and got happier, does that way make more sense? Yeah? Let's keep doing that then. So for H2, here's a hydrogen. How many valence electrons does hydrogen have? 1. And the formula is H2, so that means we have another hydrogen over here. It also has 1 valence electron. So what are they going to do? They're going to share. They only have 1 each to share, but that's enough. Hydrogen is satisfied by making 1 bond with another atom. That's all it's looking for. It just doesn't like to be by itself. We already did fluorine, and we don't have an unlimited amount of time, so I'm going to skip the F2. Let's go to H. So we were just looking, let's go to HF. We were just looking at H. It has 1 valence electron. And what about fluorine? It's got 7. 1, 2, 3, 4, 5, 6, 7. So it's got this 1 odd electron over there, and hydrogen has an odd electron. And so they're going to share. The hydrogen now counts both electrons in that bond and says, great, I've got 2 electrons, I look like helium. And the fluorine counts both of the electrons in the bond, plus its lone pairs. These are called lone pairs, and this is a bonding pair. And fluorine says, woohoo, I look like neon. I feel better about myself. You know, I'm still not in the cool group, but I look like them, and so that's awesome. How about CH4? Let's find some space. Over here, maybe. Well, here's carbon. How many valence electrons does carbon have? 4. So when we draw these, let's draw one in each of the positions before we pair things up. And that actually does represent something about how the electrons actually are. And then it says H4. So let's put a hydrogen over here. And we've been doing hydrogens. We know they each have one valence electron. So this hydrogen is going to share an electron with the carbon. And then up here, now it's more convenient to draw hydrogen's electron on the bottom. And it will share. How many electrons does carbon have right now in this diagram? It's got 6. It started with 4, and so by sharing, it's being able to count more. It's getting closer, but it's not done yet. So then over here, we need another hydrogen. I'll put that too close. Another hydrogen with 1 electron, and it will share with carbon. Now carbon has 7. Each of the hydrogens has 2. The hydrogens are being satisfied. So we need 1 more hydrogen in here. And it will share with carbon, and now, everybody's happy. This carbon counts all of these bonding electrons as belonging to it. 2, 4, 6, 8. 8 electrons. Any questions? So it's a little bit like putting a puzzle together, arranging these so that they can share electrons and have 8 valence electrons. Okay, let's draw a Lewis structure for carbon dioxide. Ooh, they gave us the name instead of the formula. What's the formula for carbon dioxide? CO2. 2 because dioxide. Well, let's see. Let's write a carbon here in the middle. And we were just looking at carbons, and we know they have 4 valence electrons. And let's put an oxygen over here. How many valence electrons for oxygen? 6. 1, 2, 3, 4, 5, 6. So the oxygen will share an electron with the carbon. So that's good. Is the oxygen satisfied now, though? No. Well, let's do the other oxygen. It says there's 2 oxygens. Let's put the other oxygen over here, trying to be symmetrical. 1, 2, 3, 4, 5, 6. So this could share with the carbon. Is anybody happy? No. We don't have any more atoms to add in there. So what could we do? How about if we shared more? There's this electron over here and this one over there. What if they shared those 2? Now oxygen has 8, doesn't it? Because all the electrons that are shared get counted by both atoms. Is the carbon happy yet? There's 2, 4, 6, 7. But look, there's this guy, and there's one over here. Maybe we could do the same thing over there. Oh, now everybody's happy. That's kind of a weird looking structure. Let's draw it a little nicer. So between the carbon and the oxygen, there are 2 pairs of electrons that are being shared. So that's 2 bonds. We call it a double bond. And this oxygen over here is also sharing 2 pairs of electrons with the carbon. And then I'm just going to copy down those lone pairs that we had. And now it's a little easier to look at. We can, fat one. We can see that there's, this counts as 2, 2, 4, 6, 8. The carbon's happy. Kind of looks like a cat. 2, 4, 6, 8. Those are not whiskers. And this oxygen's happy, 2, 4, 6, 8. So sometimes the atoms get a little creative and they share more than just one electron from each. This is called a double bond because there's 2 bonds. It's sharing 2 pairs of electrons. So there are single bonds where we have 1 pair of electrons shared, like in a hydrogen molecule. We can have double bonds where we have 2 pairs of electrons that get shared, like in carbon dioxide. And we can also have triple bonds where we get 3 pairs of electrons that are shared. And this is what happens with nitrogen. Nitrogen is one of those diatomic elements. So let's look at how this comes together. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. And the other one has 5. So they're going to get together, they'll share that one. That one's kind of obvious. That's not enough. So they could share those, and they could share these. And now, even though they only have 10 electrons between them, they can count some of the shared ones get counted twice, and so it kind of multiplies things. So this nitrogen counts each of the electrons in the bonds. 1, 2, 3 bonds is 6 electrons and its lone pair, 8. The other nitrogen has 2, 4, 6 from the bonds, and the lone pair is 8. Any questions?
So if you're writing that out, you write that N with 3 lines in between it, and where would you put the addition?
I would put the dots probably over here, like this, just because that looks nice. But if you wanted to put them on the top, or if you wanted to put these on the bottom, it doesn't matter. It's all the same. This is not a preferred method of showing a Lewis structure just because it's all kind of scattered about. But this is a nice way to figure out what the Lewis structure is. Any other questions? There are some exceptions to the octet rule. I'm just going to tell you about them. I'm not going to test you on them. Boron tends to form compounds where it only has 6 electrons, like in boron trihydride. Why? Well, I think the simplest explanation is boron is one of those little atoms, and so it has some exceptions. There are also molecules that have an odd number of electrons, like no nitrogen monoxide. Oops. Like here, nitrogen monoxide. The nitrogen has 5 valence electrons. The oxygen has 6. 5 plus 6 is 11. You can play with the dots all day long, but you can't make it come out so that each of them has 8. So there are exceptions, but we're not going to do anything with them. Let's do cyanide. Let's do this guy on the bottom.
What was the note for just before the resonance? Molecule shows resonance.
You know, I may have forgotten to delete some things from the notes. Let me look.